Gomez. Voilà. Ci parlerà appunto di PMSS, le ultime novità che sono state introdotte. Dentro sarà in inglese. Grazie.
Good morning, everybody. I switch in English. I don't speak Italian. Sorry. I hope it's okay for everybody. So I am Felix Gomez. Today I represent the house of Aria Technology, based in Boulogne-Billancourt, next to Paris. And I'm going to give a brief talk about PMSS evolutions over the last year. So let's start with the basic. So what is PMSS? The PMSS is a chain made of two models. The first one is parallel microswifts, and the second one is parallel microspray. So parallel microswift is a 3D diagnostic meteorological model, specially designed for urban applications. It takes data from surface stations, LiDARs, SODARs, and it generates three-dimensional fields of wind, temperature, and turbulence. As we can see, for example, this is an example in this picture. Maybe I can have a laser. Yes. So on this picture, we have an example of urban application, and we can see a wind slice near the ground, and we can see how the urban shape is interacting with the wind flow. So we have wake zones, circulation zones, etc. Then we have microspray. It's a three-dimensional Lagrangian model, dispersion model. Normally it's a video, so do you know how I can run the video? Normally I should have to click on it.
Okay.
I should be able to click on it to display the animation. Well, never mind. It's okay.
We trust you.
Doesn't matter.
We trust you that you don't make it.
So everybody trusts me. So it's a video. So parallel microspray is a three-dimensional Lagrangian dispersion model, also designed for air quality systems and risk analysis in urban domains. Basically, this model is computing the dispersion of pollutants generated by traffic emissions or punctual accidental releases. This should be a video, but well, this picture is showing you an example of air quality system. It's a demo on Boulogne-Billancourt, where the wind is represented by the white streamlines, and the concentration and particles in the atmosphere are represented by the colors from 10 to 100. So basically, this kind of application is able to produce maps on a daily basis on the website. So in my presentation, I will talk about PMSS evolutions. I will talk about swift momentum, which is an evolution of parallel microswifts. And then I will talk about chemistry models and wet deposition in parallel microspray. What is swift momentum? Well, swift momentum is a short name for the Navier-Stokes equation. The Navier-Stokes equation, or the momentum equation, is implemented in Swift using the RANS formulation, which stands for Reynolds Average Navier-Stokes. in Stokes, and it's implemented in steady state form. So I put here the equations of the Navier-Stokes in Rand's formulation, and basically the solution of Swifts is the solution of the system where the time derivative is equal to 0. Here we have an example of outputs provided by Swifts when we use Swift momentum. This model, well, this module of momentum was implemented during the years 214, 215 in obstacle mode and using the flat terrain assumption. The last year, we made an upgrade of this module to take into account terrain following terms and to represent the topography, the effect of the topography on the flow. Brief talk about this. Parallel microswift is using terrain following coordinates. So instead of using X, Y, and Z as a standard way of seeing dimensions, we use X, Y, and S, which is a function of the ground height and the top of the domain. And when we use this formulation, the differential operator here need additional terms related with the topography. So these terms in red are new terms implemented in the momentum solver. Please work. We don't see very well the graph here. Well, so we have implemented this last year, and we tried it on several cases. The reference case for the development was a Code Saturn simulation. So Code Saturn is a full CFD model implemented by EDF. It's a French company for Électricité de France. And on this test case, we have a hill, of course, and we have a flow from east to west. I think I'm using too much the laser because it's no longer working. And what we don't see here, but we should see it, it's a recirculation zone here. So parallel microswifts without the terrain following terms was not able to reproduce the recirculation zone. We only have a flow that follows the ground. It's not the magic one. And of course, microswifts with the terrain following terms reproduces the recirculation zone. Again, I ask you to trust me because you don't see it very well here. So momentum swift is still in beta version because the stability of the solver needs to be improved to take into account high slopes, meaning where, for example, in domains, Pyrenees, les Alpes, where you have very high slopes, sometimes the solver fails and we have to improve the stability of the solver. We also need to have an automatic way to parameterize the turbulence closure scheme. For the moment, it's done by hand. And last but not least, we have to optimize this model because we want to make it operational like Swift diagnostic. Okay, so that was the parallel microswift part. Now I switch to parallel microspray. Parallel microspray is very often in urban environments. And in these environments, understanding NOx chemistry is very important to have a good representation of the concentrations. If you just take the emission from traffic and perform the dispersion, we are wrong because there is a balance between nitrogen oxide, ozone, nitrogen dioxide. So in parallel microspray, we have a chemistry scheme implemented. It's a simple scheme. It's called Chapman cycle. It's made of two equations. The first one is ozone titration with nitrogen oxide. So it's the first equation. So nitrogen oxide plus ozone are consumed, forming nitrogen dioxide. And the second equation is the nitrogen dioxide photolysis in nitrogen oxide. So it's consuming NO2 using the photolysis, so the heat of the sun, and it creates nitrogen oxide and ozone. So what's new? Because that was already implemented in the model. The first thing is using Chapman cycle requires to use background concentration in the city, in the urban environments, and the previous version of parallel microspray was using homogeneous offsets for all the domain. And we made an upgrade to use three-dimensional background. For example, if you are coupled with a WAF and you have an heterogeneous value and vertical profiles, you can use three-dimensional information to compute the chemistry. The Chapman cycle was also upgraded into the GRS solver. I'm not going to talk about differential equation today. The idea behind this is only to show you that this is the Chapman cycle in terms of math, and the green terms here are similar. And so the GRS solver is just adding more equation, more information, and it's taking into account COV, organic compounds. Third point about chemistry. Computing a high-resolution chemistry with the Lagrange model is very time-consuming. So we have implemented a quick solution called the steady-state Chapman cycle. So it's the same equations of Chapman with the two equations we discussed in the first place. But in these equations, we consider that we are at the equilibrium and all the time-dependent terms are set to 0. So basically, with this model, we are instantaneously at the equilibrium. And the idea of this model is instead of computing a high-frequency chemistry, we are applying the steady-state solution only once before the creation of the output, and we are storing the equilibrium in each cell given the different proportions of NOx species. So this is an urban application. On the top we have PMSS running an urban case without chemistry. So it's a 1-hour simulation with traffic emissions, and it's taking 5 minutes. If we use Chapman with a high frequency, we are running the code in 16 minutes. It's on 4 core laptops. And if we use Chapman equilibrium, we are running the simulation in 7 minutes. So compared to no chemistry, we are not so far. Last bullet points, I would like to talk about wet deposition in parallel microspray. So wet deposition is a process occurring during rainfall events. When rain crosses a plume of pollutants, the droplet absorbs the parts of the gas and the particles and deposit on the ground. The mass that is taken from the plume in the air depends on the concentration of the plume, and depends also on the washout coefficient computed proportionally with the precipitation. And this gives us a decay law that describes what is the amount of gas taken from the plume and deposited on the ground. So this is an example of the previous wet deposition. I saw a slide before talking about arsenic. So this is a case where we have a punctual source here. It's an accidental release, and we have a plume in an urban environment. So on the left, we have an isosurface of concentration of the plume that describe the three-dimensional aspect of the plume evolving in the urban shape. In the middle, we have the ground concentration of this plume, and on the right side, it's the wet deposition at the ground. So what we can see is, first of all, of course, on the right side, it's cumulative deposition. So when rain comes through the plume, it deposits the deposits the pollutant on the ground, and we have a ground deposition. This model is limited because we are not taking into account the obstacles, of course. We can see that the deposition occurs where we have buildings. So basically, this model is just taking the mass from the plume and puts it right below the plume. So the idea of the evolution is to compute the rain trajectory by taking into account the properties of the droplets. It gives us the terminal velocity of droplets, and we also use the local wind computed by R.L. microswifts, and that gives us the trajectory of the droplets. And in the end, instead of making the wet deposition right below the plume, we just depose pollution at the end of the trajectory of the droplets. And so it gives us an idea. So it's the same text case. So we have a punctual source here. We have a description, a horizontal slice of the plume that shows how the concentration is moving. And we have a color fields showing three-dimensional deposition on the ground and on the surfaces. For example, here, because the wind is coming from northeast, if we are behind a building, we are protected. And finally, we tried this new model on typical traffic emission case, and this is the output of this model. So we can see that we have a deposition that takes into account buildings and small places, for example, inside these zones or here. So we have a strong effect of the building shapes on the wet deposition. Thank you for your attention. If you have any questions, that's the time.
I have one, sorry.
Okay.
When you talked about the chemistry in PMSS, I mean, you mentioned the fact that now you have a 3D background, but if I'm not wrong, you mentioned mostly for the med part. But what about the concentration, the background concentration of the species that are involved in the chemical reaction? It means that you also have a 3D
Yes.
or background, whatever, from an outer, larger simulation.
So what we did is we give the three-dimensional information of concentration species to R.L. microswifts.
Okay.
R.L. microswifts is doing 3D interpolation and extrapolation, gives this data to R.L. microspray, and when we compute chemistry in cell, we seek for the concentration of the cell of the different species. So we have a real three-dimensional array of concentration in NOx. And also the heats of the sun and the temperature are automatically computed by the code. That's
Just a curiosity, in the test case that you made in Bologna or where it was,
Yeah,
I mean, okay, that is, which is the resolution of the host model out of something like 1 kilometer or?
It's more, it's, I think it's 2 kilometers by 2 kilometers at 3 meter resolution.
Okay, but the outer model from which you take the background concentration is something which is?
It's WAF. So it's
okay, no, but the chemistry, the ozone, and the 3D background of the concentration that you use.
You mean the resolution of the?
Yeah.
I don't know.
Okay.
Sorry. Yes.
I have a question regarding the rainfall modeling. I didn't understand what time resolution from rainfall we are using.
Okay. Okay. Let's get back to this slide.
Okay, perhaps.
So parallel microspray is a Lagrangian model. So the plume is represented by a cloud of particles with positions. And each particle carries a mass. So when we have a particle, during a small time step, we compute what is the amount of mass that we remove from the particle to deposit on the ground. And the amount of mass that is taken from the particle follows the decay law that we saw earlier. So when we take this mass at every time step of the dispersion, so it's every 1 second, for example, if your time resolution is 1 second, you start from the location of the Lagrangian particles, and then you iterate with a new time step, and you resolve the trajectory of the droplet coming from the Lagrangian particle using the wind components, and you find the falling location of the droplets. And then you take the mass removed from the Lagrangian particle and you deposit on the ground.
But the precipitation you use to remove, because you use also information on precipitation.
Exactly.
Yeah, typically it's
Hourly, yes.
hourly.
So,
You interpolate it in time.
yeah, because I have an hour precipitation, then you apply to move your deposition.
The precipitation rate.
It's very difficult to have something different at the higher frequency. Yes.
Other questions?